Good afternoon, Dr. Lim. We are from Group S3G, and today I'm going to present to you the assignment design and implementation of IoT petrol station simulation with Atos, and this is video 2. Alright, for our first slide, I'm going to explain about the high-level architecture and task and justify why the Atos is important. If all the threads in our system share the exact same priority level, such as OS priority normal, the kernel would default to a round-robin time slicing. What issue would this cause? Well, this would mean our critical edge triggered tracking task could be paused mid-execution to let a non-urgent data logging task run, which represents a fundamentally flawed design, and it would be totally unacceptable. This is our priority hierarchy, and this is a diagram that we have carefully made showcasing the highest priority, which is the pump pulse ISR handler, tank level accumulation, and execution time, our medium priority, and our low priority, which is the non-critical elements in this project. Time-critical tasks, specifically the edge-triggered pulse tracking originating from our high-frequency pumps, are assigned to the highest priority relative to everything else. Meanwhile, non-real-time asynchronous operations such as packaging, transmitting data to an MQTT broker and network are isolated as a low-priority thread. This is a data flow diagram of our project where it highlights from hardware pump pulse. A physical signal is sent to the XTI interrupt where level 1 highest. This, meanwhile, triggers a ISR high priority. This posts a message to the queue, and then this is read by the MQTT thread, and that is transmitted to the cloud broker. Each layer has its clear purpose, discrete responsibilities to maximize the system stability. Each layer has a specific priority level. System protects high priority paths for real-time responsiveness, and blocking operations occur only at the lowest priority. Keeps critical ISRs and high priority tasks always unblocked. Okay, this is our slide 2 on the 2 kHz high frequency interrupt defense. Hardware latching mechanics. When a falling edge pulse arrives from a pump, the STM32's XTI hardware controller instantly latches the event into its internal pending register. This means that even if a CPU is momentarily occupied, executing a slightly higher priority hardware exception or a context switch, the incoming pulse is safely preserved at the hardware layer and will not be lost. This is our timing and waveform analysis, and this is a timing diagram where it clearly shows that the pulse frequency is at 20,000 pulses divided by the second of pump, and our pulse intervals, our interrupts arrive every 12.5 microseconds at the CPU. At 12.5 microsecond intervals, there is virtually no window between the interrupts. Thus, the system must handle the burst without dropping a single pulse. The ultra lean ISR rule. To keep the system responsive, our interrupt service routine is stripped of all its overhead. It is heavily optimized and strictly prohibited from invoking print statements, delays, complex math, or blocking logs. By restricting the ISR to merely reading a hardware timer and logging the raw pulse event, it completes its entire execution window in less than 1 microsecond, leaving significant headroom. This is our diagram on the single core versus the multi-core execution. If a single core, a maximum concurrent ISR overhead, where sum of all ISR execution times is gotten. If a single core, we must prove that the sum of ISR is lesser than 12.5 microseconds. For example, if you calculate 4 SR times 0.8 microseconds each, you get a 73% of the 12.5 microsecond window is unused. And if it's a multi-core, different cores can service different interrupts simultaneously, avoids OX mutases in ISR. Hardware atomicity is guaranteed, a thread-safe access without blocking, and it uses hardware atomic operations to safely update the shared tank variable. So as you can see, a multi-core execution is much better, much efficient compared to the single core. This is our slide 3, where I shall explain thread purposes and the banishing of polling. These are the 4 threads used in our project, where thread 1 is the task, thread 2 is the MQTT task, and thread 3 is the pump control board 1, and thread 4 is the pump control board 2. Every single thread we have created has its designated, sandboxed technical purposes, and explicitly calculated stack size to prevent a stack overflow, and a precisely defined priority level relative to the rest of the ecosystem. Awaiting events versus polling. The defined characteristics of our threads is that they spend a majority of their operational lifecycle awaiting events inside an RTOS block state. While a thread blocked on RTOS kernel primitive, such as waiting for data to arrive via OS message queue get command, it is completely removed from the scheduler's ready list. During this time, it consumes exactly 0 CPU overhead, allowing the processor to focus entirely on other background tasks or enter a low power sleep state. Slide 4. Interprocess communication, IPC, and MQTT thread safety. The multi-thread collision scenario. If thread 1, our main tank monitor, and thread 2, our system's diagnostic routine, both independently attempt to invoke MQTT publish, at the exact same microsecond, a catastrophic race condition occurs. The serial transmission frames collide, the hardware status flags becomes corrupted, and the network subsystem will completely lock up and crash, meaning the system will crash. Architectural defense options. The gatekeeper thread pattern. Instead of allowing various threads to communicate with the network, we isolate the entire MQTT library inside a single dedicated telemetry thread. Thread hashtag 1 and thread hashtag 2 are completely barred from calling the MQTT library directly. Instead, when they need an update, they can safely push their data packets into a thread-safe RTOS message queue. The single telemetry thread sits blocked on that queue, safely pulling in messages out one by one and serializing them sequentially over the network. This completely avoids race conditions and solves the problem. So, this is our 5th slide on student checklist and technical verification. And based on that, this is my summary for our project. Our priority-based scheduling ensures critical paths are always executed. Our hardware-level interrupt latching guarantees pulse capture. Our event-driven threading eliminates wasteful polling. Our message queues decouple real-time and network layers. Atomic operations ensure data integrity without heavy locks. And ISR less than 1 microsecond. Execution always leaves 99% CPU available. For other work, MQTT serialization prevents race conditions. Thank you so much, Dr. Lim. I hope you enjoyed this presentation.